Hello, I'm Zana. I'm a PhD student at Harvard. In this video, I will present our paper To Trust or to Think. Cognitive forcing functions can reduce over-reliance on AI in AI-assisted decision-making. From loan approval to disease diagnosis, people are increasingly making decisions while assisted by AI. By combining two types of intelligence, these emerging human and AI teams were expected to perform better than either people alone or AIs alone. Recent studies, however, show that although human and AI teams typically outperform people working alone, their performance is usually inferior to the AIs. Looking at the human and AI team performance on instances when the AI is incorrect, we notice evidence that people over-rely on the AI. They accept AI suggestions even when those suggestions are wrong, and they would have made a better choice on their own. There is evidence that even when the AI provides explanations, people still over-rely on it. In our study, we introduced interventions that reduce over-reliance, or interventions that improve human and AI team performance on instances when the AI is incorrect. How did we achieve that? We first asked why people over-relied on the AI in the first place. We posit that the dual process theory provides a useful lens through which to understand why people over-rely on the AI and why explanations don't help. Because evaluating every AI suggestion and explanation requires substantial cognitive effort, or System 2 thinking, people develop heuristics on whether and when to follow AI suggestions. If that is so, if people can be induced to engage in more analytical thinking when processing AI recommendations and explanations, they will notice AI mistakes. Thus, over-reliance will decrease. But how can we compel people to think? A number of approaches have been explored in other domains for engaging people in more analytical thinking. One of the most promising appears to be cognitive forcing functions, interventions that are applied at the decision-making time to disrupt heuristic reasoning and thus cause the person to engage in more analytical thinking. Examples of cognitive forcing functions in the medical domain include diagnostic timeouts, checklists, or asking a person to explicitly rule out an alternative. Bringing these insights in the context of human and AI decision-making, we designed cognitive forcing function interventions for explainable AI systems and investigated whether they reduced over-reliance compared to simple explainable AI approaches, which are common approaches that are used in explainable AI. Our first hypothesis was, compared to simple explainable AI approaches, cognitive forcing functions will improve the performance of human and AI teams in situations where the AI's prediction is incorrect. To put it differently, if people are compelled to think, they will notice and override AI's incorrect suggestions. Our second hypothesis was, there will be a negative correlation between the self-reported acceptability of the interface and the performance of human and AI teams in situations where the AI's prediction is incorrect. In other words, people will not trust and prefer interventions that make them think. To test these hypotheses, we designed a nutrition-related test where, given a plate, participants had to replace the ingredient highest in carbs with an ingredient low in carb but similar in flavor. The explainable AI category consisted of two common designs on explainable AI literature: explanation and uncertainty. In the explanation condition, people saw the AI suggestion and explanation as soon as they were presented with a question. In the uncertainty condition, in addition to the suggestion and the explanation, people also saw the confidence score of the AI. Cognitive forcing functions category included update, wait, and on-demand conditions. In the update conditions, participants made the decision without assistance from the AI. Once they saw the AI suggestion and explanation, they could change their initial decision. We hypothesized that participants were more likely to notice AI's incorrect suggestions, having made the decision on their own first. Whereas participants in the wait condition waited for 30 seconds before seeing the AI's explanation. While waiting for the AI, we hypothesized participants would form their own decision, thus will rely less on the AI if its suggestion was incorrect. Finally, participants in the on-demand condition chose whether they wanted to see the AI suggestion and explanation. Here, we hypothesized that participants would engage more carefully with the AI suggestion because they requested it themselves. In addition to these total conditions, we also included a no AI condition as a baseline, where participants completed the task with no AI assistance. Our study was a mix between and within subject design. Each participant interacted with two conditions. The overall performance was the percentage of optimal replacements, or the percentage of total questions in which participants correctly identified the carb source and the optimal replacement for it. For other metrics, please check out our paper. Subjective ratings, such as trust and preference, were collected post-interaction. As previously described, we experimented with 3 categories and 6 total conditions. We ran the experiment on mTurk with 199 participants. The results of our experiment showed that participants in the cognitive forcing functions over-relied less than participants on the simple explainable AI conditions. In other words, cognitive forcing functions significantly improved performance of the team when the AI was incorrect. Supporting hypothesis 2, however, we noticed that people's acceptability of the interventions that compelled them to think was significantly negatively correlated with their performance when the AI was incorrect. To put it differently, people trusted and preferred less the interventions that made them think more. We are aware that interventions may give rise to or exacerbate existing inequalities. Because we introduced cognitive forcing functions as interaction design interventions, we also audited if these interventions benefited different groups of people similarly. A relevant individual difference for cognitive tasks is the need for cognition, the intrinsic motivation to engage in effortful cognitive activities. Thus, in our audit, we were interested to see whether our interventions benefited people low in NFC as a more disadvantaged group in this context, and people high in NFC similarly. Our results show that our interventions benefited the already advantaged group, the high NFC group, significantly, but the benefit was not significant for people low in NFC. To summarize, we introduced the concept of cognitive forcing functions as interaction design interventions to reduce over-reliance in human and AI decision-making. Our study showed that cognitive motivation moderates the effectiveness of explainable AI solutions. Hence, in addition to designing useful explanations, explainable AI researchers should ensure that people will exert effort to attend to those explanations. We introduced internal auditing as a mechanism for guarding against intervention-generated inequalities in AI-assisted decision-making. We demonstrated the importance and the feasibility of conducting such internal audits. Our study has limitations. First, cognitive forcing functions reduced over-reliance at the cost of perceived usability. Consequently, cognitive forcing functions may find less adaptation than simple explainable AI solutions because users will resist them. We believe that adaptive strategies where cognitive forcing functions are employed only on the instances where the AI is most likely to be incorrect may be one way of ameliorating this limitation. Second, our interventions increase the performance gap between the two NFC groups. Further research is necessary to find interventions that benefit people low in NFC even more than cognitive forcing functions. Finally, the experiment was conducted in a single non-critical domain. Additional work is needed to examine whether our results generalize across domains and settings. Please check out our paper for more details.